Hello, hello. We are recording. Welcome, one and all, to Facet Nation, a Gemmology podcast. I am Lucinda, FGA.
And I am Simon, FGA, DGA. I can't
All
believe we're
right.
still doing that. We might have to stop
I
doing
know.
that.
We need to stop doing that. We're becoming braggarts.
Yeah.
But today I think our qualifications are important because this is possibly the heaviest episode we have done yet. Strap in, y'all, because it is time for materials and structure.
Yeah, the scary thing is it's only the heaviest episode to date. It's going to get worse.
Yeah, this ain't nothing compared to, I mean, this
the
is still,
gap.
this is foundation stuff still, more or less.
I suppose it is, yeah. I mean, it's like bloody GCSE science, really. It's just heavy for idiots like me.
But Simon has done an excellent job noting everything from the course notes that you need to know. We're going to try not to be as funny or tell as many off-piste jokes as usual because...
Although we can't really help being funny, can we?
I mean, we just are who we are. What can we say?
You know.
We're just so charming.
Yeah.
I'm on my first glass of wine, so let's see how this goes.
Okay.
So, Simon, what aspects of materials and structure are we covering today specifically in case people are planning their revision?
So we're basically going to talk about chemical elements and atoms and how they sort of bond together. It's GCSE science, basically.
And it actually is more interesting than I initially thought it would be when approaching it. But a lot of that, I think, comes from giving elements personalities, like bringing a little bit of your own humanity into it. Simon has a great scandalous story to help him remember some parts of this. Beryl and Boz and Miss Peridot.
Yeah.
I read that. I was like, no wonder everyone hates Peridot.
Yeah.
So much for the sisterhood. Anyway, we will get into that. First up, very basic definition. This is a definition that has come up, I think, a couple of times on exams in the past, certainly in ours, in our foundation exam. And I remember looking at it and thinking, I know what this is, but I don't know how to articulate it. But Simon, what is an element?
A chemical element. So chemical elements are basically the raw ingredients of everything. Like everything you see around you is made of chemical elements. And an element is a substance entirely composed of a chemically identical atom.
Yeah, so word for word, y'all. Got to know it. And then within that, so you have your elements and then you have your atoms. So an atom is the smallest unit of an element that can retain that element's properties. So if you think, like, I almost want to give like I said we weren't going to go off piece, but for example, if you say element A is sticky and smells like eggs, this is my cat Franz Fanon, then an atom would be the smallest bit of that chemical A that is still sticky and still smells like eggs.
Okay.
Is that helpful?
That is quite off-piste, but I get it, and that is quite good. Yeah.
Obviously, in life, the elements have really boring properties.
Why sticky and smelling of eggs?
I don't know. It's been a long day, Simon. I went to bar.
Okay, fine.
I exercised today, okay?
No, well, you know, it always makes me go a bit weird when I do exercise too.
So aside from being sticky and smelling like eggs, atoms are extremely small. I would say that's kind of their defining characteristic.
Yeah, no, we're not talking like small, like I don't know, something small. We're talking like fucking small, like
but they are not
so small that you can't even fucking see it, even with microscopes.
Not even close.
Shit, it's like wildly small.
But they are also not the smallest thing that we're going to talk about today, because there are smaller things, and those are called subatomic particles. And I like them because they have charges. So some of them are American and some are British. Some are, which is to say, some of them are positive, some of them are negative.
Which nation is positive and which nation's negative?
Obviously, America's positive.
Oh, you're positive because you're the best at everything.
Well, we're a very glass half full people.
Okay, no, you're right. We sort of defer to the misery.
And then we have, I don't know what nations should be the neutrons, the people in the middle.
The Swiss, they're always the neutral ones.
That's true.
Yeah,
that is true.
Countries beginning with S, they don't participate in any anger.
Oh God. Sorry, my cat. Ignore that thump. Everything is fine.
Okay, good.
So, so we've got three types of, to recap. We have chemical elements, which are made up of atoms, which are made up of subatomic particles, which are organized in a very specific way. Simon, take it away. Set the scene for us.
So right in the center, the nucleus of the atom are the protons and the neutrons. Now, the neutrons, handily, are neutral, and the protons are positive. So an easy way to remember that is neutral, and P for positive. There we go.
Yeah, like pro, like you see the pros of things.
Yeah, positive.
Yeah, love that.
And then around that nucleus, is...
Oh, I forgot about these.
I think you were going to tell us what's around the nucleus.
So around the nucleus are electrons, and these are like, I always think of them as kind of busybodies. They're very negative. They're kind of the curtain twitcher of the subatomic particle, because they're always trying to get into other people's business. They're always kind of starting shit. And so a lot of what your atom is trying to do and why the world exists is because full atoms want to be zen, they want to be neutral, and electrons just keep fucking it up for them. So the whole name of the game is to trade and buy and sell and share electrons until everything is stable and nobody has a charge.
Absolutely. So a complete atom, as in its normal state, is neutral because it has the same number of positively charged protons as it does negatively charged electrons. So they sort of cancel each other out and make it neutral. Now, the number of each of these things, subatomic particles, that each atom or element has is handily put together in a thing called the periodic table, which you've probably heard of.
It was definitely in the back of your chemistry textbook. Whether you looked at it?
There's always questions about it on University Challenge. So if you can learn the periodic table, that's some points you could get while you're watching University Challenge, which is how that's my yardstick for how intelligent I am. If I can get 3 or 4 questions right on University Challenge, I feel pretty clever that day.
It's just memorization of the periodic table. But it is important memorization. Yeah. It's less important, I would say, to know the numbers than to know the letters.
Yeah.
Like
I don't know. The numbers are quite important as well.
I don't know.
Fair enough. But
we agree to disagree, and we don't have time to argue about it right now.
True. So the periodic table basically puts all of these elements in a handy sort of number order for you, and each number of an element relates to how many neutrons, protons, and electrons that element has. Strictly speaking, the number refers to how many protons the element has, but when it's being neutral, it obviously has the same amount of all of them.
Yes. I'm going to read a sentence right now. If the number of electrons change, they become ions. If the number of neutrons change, they become isotopes. Simon, tell me more.
I don't know there's much more to say about that. That's absolutely right. That's correct.
Great.
So basically, if we take carbon, for example, now carbon's quite an important element.
I would say the element.
Would you?
I think so, but okay. Agree. Again, we don't have time to discuss it. So
De Beers have a wing of their company called Element 6, which is the one that makes the synthetic stones, I think. Which leads me on to say that carbon's atomic number is 6. Element 6. So that means it has 6 neutrons, 6 protons, which reside in the nucleus, as discussed, and then those 6 electrons whizzing around the outside in sort of concentric rings. Now, we don't refer to them as rings, we refer to them as shells or orbitals. The number of electrons that are in each orbital is sort of has some uniformity to it. So the first ring basically has 2 electrons, and then it's full. And then how many are in the second ring? Orbital, not a ring. Call it an orbital.
8.
8, yep.
Then 8.
Yep.
and then 18. So it's 2, 8, 8, and 18.
Yeah, and then I think it's 18 and then 32 and like. But for the purposes that we need to know, we can sort of kind of stop at 18, 32, that sort of thing. We're not going to be talking too much or be too concerned with elements that go much higher than that. Is
Yes.
it like if you really want to? I don't want any people going like, oh, that's not strictly true. So I'm going to say now that isn't strictly true, but for our purposes and our purposes of understanding and what we need to understand, it goes 2, 8, 8, 18, 18, 32. So anybody that wants to argue, you're right, and I accept that you're right, but we don't need to know that. Right.
Simon is dreading the fan mail. He's dreading it.
Yeah, well, I saw people going, oh, that's not true, actually. So, yeah, 2 and then 8. The next one's 8 is full. Leave me alone.
Well, and I think there are going to be some elements, and we'll talk about some of them later, that are really important to know a lot about. And it's important to know how many electrons are in each orbital. But for the most part, the most important thing is just to understand broadly how it works. And the way that it broadly works is that we are looking at these orbitals because, as I said before, electrons, they've got a terrible personality. And if their orbital is not full, they get narky and they are looking to make some changes.
Yeah, they get super narky, actually. And they're going to go hunting for those extra electrons. Or even they're going to be like, these fucking electrons, I've got too many of these. Fuck off.
Get out.
Because my inner orbital could be much happier if you didn't exist.
They're terrible, really.
Yeah, right. Yeah, they are. So
very rude people.
Let's look at carbon again. So it has 6 electrons in total, right? So that's 2 on its inner shell and then 4 in the next. So if it's full at 8, carbon wants 4 more, basically, and then it's going to be happy because it's got like a full outer shell. Now, basically, that number 4, the amount that it needs or wants to get rid of, is called its valency. So carbon has a valency of 4.
Yeah, that's what it's playing with. So if you think of it as, this is what it's willing to buy or sell. It's willing to take 4, it's willing to get rid of 4, and it's looking for another element that's down to make a deal.
Absolutely. So I like to think of carbon as a sharer.
That's nice.
So carbon likes sharing its electrons, whereas oxygen, which is atomic number 8, has 6 electrons in its outer shell, and therefore a valency of 2.
And a valency, and as Simon said, so a valency is the number of electrons that an atom needs to gain or lose to be happy. So oxygen is looking to take. It wants more. Oxygen
is like literally roaming around because there's shitloads of oxygen everywhere. It's roaming around and it's taking electrons off fucking everyone. Yeah. And so oxygen is basically the best taker, the best oxidizer that there is. Right. Yeah. So oxygen is going to take your electrons better than anybody else. Like, it's that bloke that you're worried about your wife running off with, because he's fucking run off with everybody else's wife. So you're just
next in line, man.
Don't get that motherfucker near me because he's running off with everyone's wife.
And when he does run off with your wife / electrons, there is actually a name for it because it happens so much. You have been oxidized. That is oxidization.
Oxidized. Yeah, exactly. And oxidation is a chemical process by which an atom, ion, or molecule loses electrons. Yeah. So something else I want to say, like, everyone's going to go, I'm paranoid about this sort of thing. Everyone's going to be like, oh, well, actually, there's a better oxidizer than oxygen.
I think maybe you should just chill, Simon.
Well, no, I can't chill because I don't want people thinking that I think oxygen is the best oxidizer in
when
the
that's
periodic
clearly
table.
not true.
Because it's not. Fluorine is a better oxidizer because fluorine only needs 1 electron in its outer shell. However, oxygen is much more abundant, so it gets about more. There's more of them. They're going to nick more stuff because 47% of the mass of the Earth's crust is basically oxygen. So it's all over the place. So it's
especially where shit's growing, right?
Exactly.
Crystals
so it's going to be nicking electrons all over the shop. unlike fluorine, which is much less abundant, and despite it being slightly better, it's not so much of it. So there we go. We made that clear.
Thank God. So don't be writing Simon saying that he doesn't know, okay? Because he does. He knows all about oxidation.
Exactly. Thanks to another podcast, actually.
Oh, really?
Yeah.
Give them their due. Who are you listening to?
It's called, I can't remember what it's called, actually. James Fodor is the bloke that presents it. He's an Australian guy. It's actually really, really good. And if you are interested in learning about sciencey shit, then I would listen to it. So shout out. I think it's called The Science of Everything is what it's called. It's really good.
Great. And we will, I mean, at some point, maybe closer to exam time, we'll do kind of tertiary revision recommendations. So books that you can read or listen to, podcasts you can listen to, documentaries you can watch when you don't want to be fully revising, but you want your brain engaged in Gemmology because...
And you just want that sort of snappy revision stuff. Yeah, rather than listening to this whole episode of us digressing every 5 seconds.
We are not digressing because do you know what, Simon? Other elements have a valency of 2 and 1, but oxygen is better due to the proximity of the orbital to the nucleus, which gives it more attracting power. Can you explain this to me more?
So the closer the orbital is to the nucleus means it's got a greater attracting pull. So
if we're in that 2, that 2 is like the strongest.
Yeah. So because oxygen's valency is only its second ring, it's got a low valency, and also it's very close to its nucleus, so it's strong at attracting things, and it really wants to attract things.
So it's basically irresistible because there's loads of it. It's got a very attractive valency state, and it's got a convenient number.
Exactly.
Which is nice. Good for oxygen. It's all right for Sam, isn't it?
Absolutely.
So in brief, and we've touched on this, but in one sentence, what is it that atoms are doing?
They're donating, accepting, or sharing electrons. And when they do this, they're known to be bonded to one another. Which
I think is really creepy because it's kind of the equivalent of me saying hey, would you like to borrow my jumper? And then we have to be best friends. And as long as you're wearing my jumper, I'm following you around.
I suppose in some situations, both of you might get in the jumper at the same time.
That is true. That is so true.
In some bonds,
you're sharing.
You're actually sharing the jumper.
And there are 2 kinds of bonds, which we will discuss now. The way that I like to think of it is one is like monogamy and one is like polyamory.
Okay.
So when we talk about an ionic bond, this is when chemical elements donate or accept electrons from each other. One is a metal and one is a non-metal. So ionic bond, one non-metal, one metal. And then they're electrostatically attracted to each other. So this to me is like monogamy. So one element gives its electrons to the other and then they stick together. One is a metal, one is a non-metal. The exchange is complete and it bonds them. Very nice. But it's a giving. It's not a sharing.
It's not a sharing. No, it's definitely a gift it's a gift. You're donating or accepting from another. Yeah.
Yes. So basically oxygen comes to you and says, give me your negativity. And you give oxygen your negativity and then oxygen is your best friend.
Yeah. Very nice.
Yeah, this is where shit gets creepy. The covalent bond. So covalent bonds, as I say, they're very strong. They can occur between non-metals, but this is where everybody is sharing. It's like a thruple. Electrons are going back and forth. Everyone is happy, but there's also a little conflict because you give your electron and then you have to stay really close to take it back to make sure you get it back. So I always view covalent bonds as they're a little bit more chaotic, or they're actually stronger because everybody's watching each other really closely.
Okay. Yeah.
No shade to polyamorous couples. Yeah. No shade.
Okay.
And there is one very famous covalent bond, very crucial to the way the whole world works. Which one is that, Simon?
That would be diamond.
Mm-hmm.
So diamonds bond covalently, and we're back to carbon as well. So Diamond is made solely of carbon, and it forms a very strong covalent bond with. So a carbon atom forms a very strong covalent bond with 4 other carbon atoms. These bonds are, like I keep saying, very strong. They're very symmetrical with equal angles and distances between each atom. And this bonding formation is known as tetrahedral covalent bonding. And these little units of tetrahedral units repeat throughout the structure. And it is this that makes diamond so sort of extraordinary in all of its ways, basically.
Mm-hmm. And as Simon says here, all orbitals are happily full and sharing amongst themselves like a lovely kindergarten class.
Yes. Although most of the time when you see kids in schools, they're normally spitting at each other and stuff.
Well, I'm a proton, so I think that they are just growing through play.
Of course, yes, of course you do.
So we've looked at we've got our elements, we've got our atoms, we've got our subatomic particles and all of their drama. So now let's zoom out into what a gemstone actually is. So a gemstone is basically a group of chemically bonded atoms. Some are just carbon, so that's like diamond, but some are compounds. And a compound is a mixture of different elements with all of its atoms. And in general, because it's a numbers game, really, atoms like to be bonded in an orderly fashion. So they like to find who they're going to bond with, and they all like to be bonded in the same way. Because if you think about it, it's atoms repeating in a pattern. And so they like to repeat and mix in the same way amongst themselves, whoever they decide to bond with. If you do bond in this kind of neat, orderly, repeated pattern, you are crystalline, which means you possess a crystal structure. Define it for us, Simon.
So a crystal structure would be a regular, repeating, 3-dimensional arrangement of bonded atoms.
And again, really important definition to know. So that's one of the ones that you want to write down on your flashcard and just get it off verbatim. They'll ask you crystalline, crystal structure, crystal lattice, which we'll talk about in another episode. But all of those, it's really helpful to just know verbatim what that is. Especially because you can kind of start to confuse them amongst each other.
Yeah, you actually can. Yeah, and you start to think like, you need to be pretty clear and definite about these sorts of definitions.
Yes, especially because not everything is crystalline. So you start talking about the opposite of crystalline, which is atoms that are bonded in an untidy or disorderly crystal structure. And these are called amorphous. And this can happen for a few different reasons. Usually it's because they have become a solid too fast, essentially. They become something too fast. They don't have time to crystallize in that really neat structure. So glass, for example, is an amorphous material. And determining whether something is amorphous or crystalline is really, really important. And there's a couple of important things to remember when you're testing. Simon?
So, crystalline materials possess directional properties, whereas amorphous materials do not possess directional properties. So we're talking like cleavage, for example. Mm-hmm. So
Theochroism.
Yeah, that sort of thing.
And these are, because so much gem testing is looking at the way that a material is reacting to light and turning it and flipping it, deciding whether something is amorphous or crystalline is actually a really helpful way to just eliminate a big chunk of stuff. Because once you know that, you can see it very clearly on your polariscope, and then you're good. You know where you are, approximately.
Exactly.
We will talk about, we'll talk about amorphous materials for sure, but the reality is that most solid materials are going to be crystalline, in particular the materials that you're looking at in a Gemmology course, including one of my favorites. A classic, a stone cold classic.
Quartz.
Yeah, tell us about it, Simon.
Quartz is a crystalline structure of chemically bonded atoms of silicon and oxygen. So silicon dioxide. Now, silicon is an opaque solid and oxygen is a colorless gas, but combined they become a transparent, colorless crystal and possess completely different properties to their constituent parts.
Which is pretty cool if you think about it.
It's actually quite when you actually think about it, you're like, what?
No, I know. And then
All
quartz is
because
especially
electrons
cool.
are just pissing about. This gas and this solid becomes something completely different just because of electrons mucking about.
And then if somebody else drops by, it becomes purple or it becomes yellow, or then the heat activates and it becomes something else entirely. It's so cool.
Exactly.
So here's another important definition, which I think was on one of our exams as well. And this is a mineral, right? What is a mineral? A mineral is inorganic, crystalline material formed by geological processes. So it's a three-pronged definition. It's important to know all of those. So minerals, inorganic, crystalline, formed by geological processes. If they are formed with no human help, they are natural. New minerals are formed by weathering, erosion, flooding, volcanic eruptions, or plate tectonic activity, which basically fucks with the atoms. It melts them, they get scattered, they reorder, and they crystallize as something else. So big catastrophic events, extended heat and pressure, all that.
Yeah. And so when we're talking about gem formation and gem crystallization, there are some key elements that are present in the Earth's crust. So basically there are 92 naturally occurring chemical elements making up the rocks of the Earth's crust, right? Only 8 of these make up 99% of the mass of the crust. And they are, in descending order of abundancy, oxygen, which we mentioned before, 47% of the mass of the Earth's crust. Then silicon, 28%. Then down to aluminium, 8%. Iron, 5%. Calcium, 3.5%. Sodium, 3%. Potassium, 2.5%. And magnesium, 2%. Now, if you add all those numbers up, it comes to 99.
And so that explains essentially why when you start looking into the makeup of most gemstones, you're going to see the same names repeating over and over and over again. And it's probably going to be something on this list. Before we start talking about different ways to categorize them and what your kind of most the popular ones are, Simon, I really like your mnemonic here. So how do you remember these guys?
So for those 8 elements that make up 99% of the mass of the Earth's crust, there's a little mnemonic that you might want to remember, and it's only strong athletes in college study past midnight.
Very nice. I think the most important thing to remember, I mean, oxygen is just it's so much higher than everything else.
Yeah, it's everywhere, which is why everything's being oxidized all the time.
And silicon as well at 28%.
Yeah, which is quartz, which is basically the most... Yeah.
Sand is quartz. I mean, it's everywhere.
Everything's bloody quartz. Dust is quartz, yeah.
Well, and the great thing about these elements and how common they are and how much more common they are is that they've given us a really interesting way to categorize stones by their chemical makeup into like very neat categories. So, Simon, what are those categories?
I was just going to mention about the transition elements as well. So there's a whole other set of elements that we should speak about that are also very important.
Oh, sorry, I had my notes mixed up.
In the wrong order.
JK. Yeah, I'm back.
Enough.
I'm back in the
okay.
game.
Okay, good, yeah. There's some other there's some other elements that are very important in gemstone, in the makeup of gemstones. And they would be the 8 metallic elements, which are basically the ones that cause the colour. I have a couple of favourites. You probably do too.
I certainly do.
And the 8 metallic elements that basically cause colour in gemstones are titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and copper.
Very nice. Simon doesn't have a mnemonic for this except the very Roman numeral-esque.
I used to say in my head, TVC Mcnook.
I did not do that. I just memorized what color each one imparts, and then it kind of gives you a sense of their personality. So titanium is blue. I always think of what's that French movie, Titane, where she's like obsessed with cars or something. I never actually watched it, but that's how I remember. I always think of like blue chrome. Vanadium.
No, I don't know what you're talking about. When was that made?
It's very art house. You wouldn't know it, Simon.
Oh, is it? No, I have a very low capacity for anything arty. Those 4 years in drama school did nothing for my...
Nothing.
Yeah. Anyway,
Vanadium is usually purple. We were introduced to this a little bit later in diploma, especially when you're talking about synthetic VFF, colored, quote unquote, color change sapphires. But I always think of this as like the punky little cousin. Then we have chromium, the big diva, red and green. Manganese, my personal favorite, because manganese never gets the credit it deserves.
No.
And it causes pink and orange. How nice is that?
You were just saying you don't fucking like paparazzi the other day.
Well, I know, but I love rhodochrosite. Justice for rhodochrosite.
Okay.
Then iron, and iron's a really heavy hitter. So red, green, blue, and yellow. Cobalt, that really intense blue, which is easy to remember because cobalt blue is just its own thing, right?
Yeah. Like in natural, you get natural cobalt blue spinel, then you're in for some money.
Yeah. Nickel, green, easy to remember because it turns your finger green. And then copper, blue and green. Easy peasy.
Yeah.
And there's a couple of other elements that are important. So carbon, obviously, which is diamond, and then the reasons that diamond will have color as related to elements. So boron, that's your blue babies, and then nitrogen, that causes your yellow in a diamond.
So these elements basically, and the way they're bonded, determine the physical and optical properties that they exhibit, including the color, the luster, the refraction, all that stuff that we previously spoke about in episode 3.
Yeah. And now we get to talk about what I was talking about before, which is this really neat way to categorize them. So there are 4 categories. Take it away, Simon.
So, yeah, most of the gemstones consist of at least 2 of those 8 common elements, right? So quartz, for example, is silicon and oxygen. Peridot, for example, is iron and magnesium with silicon and oxygen. So the chemical composition of gemstones are worth remembering, as the component parts will inform how the whole behaves, basically.
Exactly.
So yeah, there are 4 main compounds we should be familiar with as the basis for gemstone composition. And the first one is...
Drumroll.
Oxides.
Yes. Oxides, I really quite like. Oxides seem to me like the kind of landed gentry of the gemstone world. You've got your hard hitters. You've got corundum, which is aluminum oxide, chrysoberyl, beryllium aluminum oxide, cubic zirconia, zirconium oxide, and spinel, which I always think is trying to usurp corundum as the top dog, but it can't because it's got magnesium. So it's magnesium aluminum oxide. And in short, an oxide is oxygen plus another element.
Yeah.
And go on.
Yeah, so oxides tend to be quite hard. So if you're looking for a durable gemstone that you can kind of wear pretty regularly and not have to worry too much about it, then go for an oxide. So when you go into a jewelry shop and you're looking to buy a gemstone, say, "Excuse me, sir, which of your gemstones is an oxide?"
I would like to see your finest oxides.
Please show me your finest oxides. I only want to buy an oxide. And see what they say. They'll probably tell you to get out, to be honest.
Absolutely. Next up, very much the middle classes of the gemstone world. These guys are the middle of the road, neither too good nor too bad. They're just right. These are the silicates. So it's actually a little bit more complicated because they are the most important gem group. But there's a few different phrases that might come up when you're talking about silicon and silicates and silica. So can you give us a brief starter for 10 on that?
I think I made some notes about this a little... Oh, no, here we go. That's it. Yeah. So silicates are effectively the most important chemical gem group because there's so many of them. Yeah. Most of the rocks that make up the Earth's crust are silicates, as well as the majority of gem material. Silicates are... like some of them are quite hard, some of them are quite durable, some of them are a bit less so you might want to be a bit more cautious depending on which silicate you go for. But
they're usually in the 5 to 8, but they're very much themselves, kind of middle of the road.
Yeah, absolutely. And I think what you were referring to is there's some distinctions that you need to remember. So silicon is a chemical element with Si as its, I don't know, what do you call that name?
Chemical symbol.
Symbol. Yeah, there we go. Silica.
Sorry, my cat Francis has joined the chat.
Oh, hi. Silica is a chemical compound of silicon atoms bonded with oxygen, i.e. quartz, right? And then silicates are a mineral group composed of silicon and oxygen, then bonded with an additional metal of some sort. So, like zircon, for example, is zirconium silicate. And why don't you tell us some famous silicates?
Absolutely. And then Simon can give you the goss after. So first is beryl. For the people in the back, this is your emeralds, this is your aquamarines. So they are beryllium aluminum silicate. Feldspar, very complicated group of minerals, but they are all aluminium-based silicates in varying kind of puzzle pieces.
Have you always said aluminium, or did you used to say aluminum?
No, it's aluminum. It's aluminum.
So why are you not saying that now?
Because I never say it out loud. I only write it because Gemme makes me do essay exams. And so I have to spell it out in my head, and it has a better ring to beryllium aluminium sounds better than beryllium aluminum.
Does it? Okay.
That's why it's more poetic. I have a degree in poetry. So
fine. Carry
on. Garnet. God help us, the isomorphous garnet series. Simon and I traumatized. To be fair, I actually have it here because I'll never forgive myself. But Craig told us, he spent a whole lovely lecture on the isomorphous series. We didn't listen, and we sat down.
Ignored him. We were like, that's not going to come up. That's a bit complicated.
No, and I was on the bus the morning of, and I was like, I'm not going to revise that. I don't want to know that. Open the exam. Second to last question or whatever is what is the isomorphous series? Draw it. And I didn't know. So I just did let me tell you about my favorite garnets.
How about no? Just write lol.
The important thing to know is they are all silicates. And when we talk about garnets, we will give them all to you and ways to remember them.
Yeah, because we're all right with it now. We came to terms with the fact that we need to know this. And then when we got onto the diploma course, we taught ourselves.
We learned it.
Yeah.
Not that it helped us. Shell. I actually got that right, so whatever. And everyone's least favorite silicate, peridot, magnesium iron silicate. I don't mind a peridot. Simon clearly hates peridot because let's just listen to the role that he has given peridot in his mind drama.
Okay, so I have this strange mind where I have to remember things in a certain way, and this may or may not be helpful to you, but the way I remember beryl and its chemical composition, which is beryllium aluminium silicate, is that beryl is married to Baz. Yeah? BAS, beryllium aluminium silicate. Beryl and Baz, they're a married couple, right? In my mind. This is where
enter Miss Peridot.
Yeah, because peridot, which is magnesium iron silicate, MIS, Miss Peridot, is having an illicit affair with Baz.
Naughty Miss Peridot. What about the sisterhood?
Exactly. What is your problem, Miss Peridot?
I mean, shame on Baz as well, to be fair.
Yeah, well, yeah, exactly. You've got no willpower, my friend.
Why does it have to be Miss Peridot?
Well, because it's the fucking letters that make up magnesium iron silicate. It's not my fault. Ms. M-I-S.
Okay. I got it. I was trying to why did it have to be her? Why couldn't it be Feldspar? But Feldspar's got its own shit going on. It's got its own feminine drama.
Very, very much so. This is like a civil war, Feldspar.
They all hate each other, I'm convinced.
Yeah.
On to carbonates. So these are kind of the hippies of the group. I don't know. I feel like carbonates and phosphates are both they're giving hippie.
Okay.
But carbonates are, I mean, I guess you guys are starting to get it now, but they are carbon plus oxygen plus a metal. And they've kind of got a lower hardness. They're not doing so well. They're the precious ones that you have to keep really safe.
The ornamental
Usually,
ones.
Yeah, 2 to 4. The kind of weird ones that your mom won't know about. What are some of your favorite carbonates?
I don't know if they're necessarily my favourites, to be honest.
Your favorite carbonates?
I do quite like a calcite rhomb.
Yeah.
But calcite is a carbonate. That's a calcium carbonate. Coral is also calcium carbonate, but is like a different
Organic
version.
secretions of calcium
Organic
carbonate.
secretions, yes.
That's what it said on the flashcards.
No, it did. You're absolutely right. From a
Hashtag never forget.
Yeah. Malachite, I actually do really like malachite.
Great
that's copper
stone.
carbonate, and that's that really nice green colour that we get from the copper. Yeah, I like malachite a lot. I like
And
lumpy
rhodochrosite.
bits of malachite. And then rhodochrosite, which you said you like, which is a manganese carbonate.
Very lumpy stones when done right. Can you hear that scratching?
Yes, a little bit. There was
Right.
a rhodochrosite like faceted gemstone in the Gem kit, and it was like basically sellotaped and glued into the box because it was so fragile and nobody could take it out in case they like busted
Not
it or
allowed.
something.
Yeah, you can get them faceted, and I feel like TikTokers really like a faceted rhodochrosite because they're this spectacular kind of red pink color, but they're basically unsettable.
I think one of the crystals in the Lego set is rhodochrosite.
That's cool. Is it botryoidal?
No, I think it's just. I think it's rhodochrosite. It hasn't arrived yet though, so we don't know.
No say.
And then
Last but not least,
your
I would say.
other hippie group is the phosphates.
Nobody really likes these guys. I would say.
Apart from all the people that are like, oh, fucking hell, I really like a phosphate. I like you always talking for other people. Nobody likes them.
Sweeping generalization.
Right, yeah, sorry, I actually do.
I just feel like they're always crumbling or there's a major ethical issue with them.
Okay.
All right. Also, they have a much lower hardness, and most 2 to 6. Also, I'd say these two, trying to tell a synthetic or treated from natural and untreated makes me want to die.
To be there. Yeah.
So who are they, our enemies?
So turquoise is a phosphate. That's a copper aluminium phosphate. You'll notice that the letters that make up copper aluminium phosphate are CAP. So in your mind, if you would like to think of a turquoise cap being worn by Miss Peridot, you will remember the chemical composition of turquoise.
That is very sweet, actually. And also ivory, which is a calcium-based phosphate, which we're going to have many episodes on, I'm sure, because there's so much going on with ivory.
Yeah, there's a lot to talk about there.
Which actually segues nicely to organic materials. So going back, what we've talked about were crystalline materials. So
minerals,
inorganic, crystalline, formed by geological processes. If there is an animal or something alive involved, we're not talking about organics. And these are their own group. They play by their own rules. Some are squickier than others, I would say.
Squickier?
Yeah, like grosser to handle. There was like a week at Gem where I was like, I'm not touching that.
It's too squicky.
Yeah, the tooth and the bone and the...
Oh, yeah, there wasn't that big fucking gnarly molar was pretty serious, wasn't it?
I'm not touching that. Something died so that could be in this room, and I'm not down with that.
Yeah, no.
But I love the first one here, which is amber, which is a fossilized tree resin. This is my favorite necklace at the moment. Beautiful Baltic amber, sun spangles in there. Warm to the touch. Love it. So it is fossilized tree resin, obviously. And it's a really good example of an organic material. It's composed of carbon, hydrogen, and oxygen atoms, which makes it...
a hydrocarbon.
Yeah, very good. Well done. What are some other organics?
Pearl, for example.
Yeah.
Classic.
Which is
sort of nacre platelets of calcium carbonates / aragonite. So, yeah, pearls, ivory, as we just spoke about. Mammal teeth is died, literally. Yeah, because it grows in a living thing's head. That's what makes it organic. Um,
When you put it like that, Simon.
yeah. Jet. That's another one. Another one.
And jet's
very
actually really interesting. So I'm looking forward to our jet-specific episode because the theory that they have on why jet exists is so gross and weird and interesting.
We must be able to find like a jet expert.
Oh, well, don't you remember Craig had that lady who did her PhD on it?
No.
Yes. So, well, don't
Is
worry,
she from
guys.
Whitby?
I'll get the goss for you.
Okay. I've not been to
Where
Whitby.
Simon
I'm quite
fails,
interested.
I come through. I
Craig
loved Whitby.
Craig used to tell us that one of the most famous things about Whitby was scampi rather than
Yeah,
jet.
because Whitby Bay is the frozen scampi brand.
Oh, is it?
You clearly don't eat enough scampi.
No.
I'm really turning out to be the girl to know in this episode. I know the French films. I know the good scampi.
Seems to be true. Yeah. Okay.
Coral is another one. So these are little polyps spitting out calcium carbonate. And just to say that something is organic doesn't mean that there have been no geological processes. Often there have been. Often something's been petrified or fossilized. It just means that at some point down the road, something alive was spitting or shitting or dying or something.
Literally that, yeah.
And then last but not least, the big humph at the end, the big letdown, rocks.
The rocks, which are basically natural aggregates of mineral crystals, referred to as mineral grains. And that's your lapis lazuli, which is actually quite nice.
Love it. I'm actually wearing some.
Bastard to decipher whether it's natural or synthetic or whether it's bloody dyed howlite or something.
Dyed howlite.
Yeah, like that's a heck of a task. But basically, lapis lazuli, don't know.
I've always said lapis lazuli.
Lapis lazuli. Okay.
I just said lapis.
Lapis. Okay, let's stick with lazuli. I'm giving up. Basically, it's a rock composed of lazurite, which is the blue bit, calcite, which are the white bits, and then pyrite, which are like the gold yellowy flecks in it. If it doesn't have the pyrite, it's probably not natural. Is that right?
Or it's been cut very badly. I will say in our diploma sets, I had the worst piece of lapis I think I've ever seen in my life. It had one tiny fleck of pyrite, like right at the end. It used to be a very expensive material, is now no longer a very expensive material. So I think you can get it in very varying qualities, to be honest.
Yeah, you could like crush it up to make pigment as well, don't they? So that a lot of the paint stuff from the ancient times is from crushed up lapis.
Exactly. Eyeshadows, cosmetics, loved it. I mean, it's got that beautiful color, right? It's
that colour's
indescribable.
actually phenomenal. Yeah, like Eve Clyde blue.
Ultramarine.
Ultramarine, yeah.
Yes. And they also will sometimes try and tell you that jade is a rock, jadeite. I'm not convinced on that one. I don't think Craig was either.
I've got
But
no
if they
opinion
ask
on
you
that.
for two, just throw in jadeite.
Okay, fine. Yeah, so something with mineral grains, basically.
Yeah. And that, I mean, what do you think, Simon? I think we're done, but was that helpful? Did that make sense to people?
I don't know. Like,
Write us and tell us. Facet Nation at facetnation.co.uk.
Yeah.
And guys, remember to hit us with your questions. We'll be doing mailbag episodes. Hit us with your comments. We'd love to hear from you. What do you want to learn about next? What are you really struggling with? People coming up to their exams in January. How can we help? What can we do? People just starting. What scares you the most?
Yeah,
Let
so
us know.
You can reach out to us on email, and that is facetnation@facetnation.co.uk, or you can drop us a message on the Instagram, which is at Facet Nation Gemmology. I've been thinking maybe we should write the word pod in that, but I haven't decided whether we should do that yet or not.
We'll think about it. Okay.
Yeah, but that's at
Think about
Facet
it while
Nation
you're on a
Gemmology.
boat.
Yeah, I'm going
Great.
on a cruise because I'm very old, so I'm going away for a bit. But
For some reason, I thought you were like going to go on a sailing boat or something interesting, but you're actually just going on a cruise.
yeah, I'm just going to go and sit in the sun and eat too much for a week, and then
nice.
come back ready and raring to go for episode. What episode is this? 5?
This is going to be episode 5, so episode 6. If Simon is not sounding rested, we'll send him back to sea.
Okie doke.
let us know. As always, thank you to you guys, our listeners. Thank you to Gem A. And thank you to Rob, our podcast dad.
Thank you, Rob, as ever.
Guys, happy studying, happy gemming. And we will see you this time next week.
Adios. Bye.
Good night.